Hey guys, this is Fred from Pretty Fly Games, and today we're gonna continue with our car AI built in Unity. Today we're gonna focus on improving the pathfinding capabilities of our car. If we have this course with the blue waypoints, then if we press play, the car will just slam into these obstacles and it will not find its way to the waypoint. So what we will do is we will implement a form of an A-star pathfinding system that allows the car to actually detect that it's stuck and then find an alternate route around the obstacle. So that's what we're going to do today. So let's start by looking at the theory behind the A-star first. So A-star is a search algorithm that is often used in games for the AI to find its path through a maze or something similar. The mathematical formula of this is this: F equals G plus H. And what it really means is that if we look at H, it is the cost from the point N to the goal. And G is the cost from the start to the point N. And F is the total cost, so it's G plus H. So that's the only math part we will actually look at this, and then we will go through it with some examples. So in our example we have a car that wants to reach the star and there's an obstacle in the way. So the first thing we do is we divide our course into a grid with tiles, and we call these nodes. So the start node here is the green one, and what we do is we use our formula. The total cost is equal to G plus H, and we record the number G value here and the H value here. So the first value up here to the right is the distance away from the start point, so it's 0. And the other value 4 is the distance to our goal, the star. So we just count how many tiles away it is. So it's 1, 2, 3 and 4. So we get the value of 4, and this total is 4 plus 0 is 4. Then what we do is we look at the neighbors, and what we have done is we have simplified this, so we're only looking at the neighbor above, the neighbor to the right, bottom and left. So if we calculate the same thing for the top one, then we have that it has a distance of 1 away from the starting point and distance of 3 to star. 1, 2, 3. So the total value is 3 plus 1, which is 4. So if we do the same thing for the surrounding tiles, the neighbors, we get a couple of options. So what we want to do is we want to pick one of them as our next step, and we want to pick the one with the lowest value. So what we do is we look at this 4 is the total value of the one above, and the one to the right is a total value of 4 as well. And the ones to the bottom and left is values 6, which is higher, so we don't pick them. So we decide that, okay, we want to go to the top one. And we also record what step number we have, so that we can retrace our steps later on. So we have our step value of 1 because we started here. Then we went up here and we got a step value of 2. And then we repeat the process by looking at the neighbors. So the neighbors to the right has a value of 4, and the reason is that it's 2 away from the starting point, 1, 2, and 2 away from the star, 1, 2. And now we have also done the same thing on this neighbor, which got a value of 6, so that's not a viable option to continue. Now we have 2 sort of options to select from, either this one or this one. So to improve the algorithm, we are selecting the value that has the lowest value of the distance to reach the goal. And in this case, as a human, we can see that, okay, this is probably not actually the best option, but for the computer, and when we program it, it will be easier. And later on we will see that this often produces the best value. But in this case, the computer selects that, okay, this is the lowest value with the lowest distance to the goal. So what we do is we again calculate our neighbors, and it only has one neighbor that we have not calculated before, which is this red zone, and we cannot walk on it, so it's not a real neighbor. So then we have to repeat the process again and look at, okay, what's the next tile with the lowest value, which is this one. So the computer will select that one, record the step number, and repeat the process by calculating the cost of the neighbors. So we have the value of 6, because it's 2 away from the starting point, 1, 2, and 4 away from the star, 1, 2, 3, 4. Now there are a couple of tiles, this one, and this one with a value of 6, but there are only 2 tiles with the second value of 4. Both of these have the value of 4. So the computer again takes a pick, and it takes this one as the point, and it adds the value of 5 here, which is the point or the order that it has stepped on. But there are no more neighbors to calculate for this one. So that means that okay, we need to pick another value from or another tile from the yellow ones. So the computer picks this one. And it starts the process again of calculating the points or the neighbors. So to the right we have a value of our cost of 6, and to the bottom we have a value of 8. And yeah, so the best option here is this one. So the computer picks that one and repeats the process again by calculating the costs of its neighbors. So by doing this, we can see that, okay, we are going to reach our end goal. And once we have reached it, we need to allow the AI to find a path from this to this. And if we would follow our steps just in the numbers that we have taken, then the AI would start here. Then we would go to number 2, number 3, number 4, and then it would drive over here to number 6, and then it would drive over here and over here, and then up. So that would be a rather strange path. What we do instead is we start at the destination, the goal, and we look at this number now. So out of from this tile and its neighbors, which has the lowest pick number? So this one has a pick number of 9. So that's the only option we have. So we continue with this one, and it has a pick value of 8. So okay, that's the one we selected, and there is only one option. So let's go to 7, and then we have our pick value of 6. So now that we look at it, okay, we have another pick value of 4. So that's perfect. We drive here. And then we have the neighbors. We have this one has a value of 3, and this one has a value of 1. So let's select the one with the lowest value. So now we have reached our point with a nice path to actually allow the AI to drive to our desired goal, the destination. Awesome. So let's look at how we can implement this in Unity. So in Unity I've set up a scene called A* pathfinding, and it uses the same scene that we had before with the oval racetrack. Now what I've added is a few obstacles, I call them roadblocks, and I've added a box collider to them, and I've also optimized the collision shape a little bit of our car so it doesn't snag so easily on other AI cars and obstacles. But still, if we run this now, we'll bring it up here, and if we press play, we will have the same situation that we had when we looked at the video. So the car will hit this roadblocks and it will get stuck. So this is the situation that we want to improve. So let's start by creating a new script, and we'll create a folder so we get a little bit better structure on our scripts. So we'll create an A* folder, and then let's start with a new script, and it will be called A* light, because we will make a light version of A star. So let's open it in Visual Studio. So the first thing we want to do is create a grid that we can use for our algorithm, and that we overlay on our course. So we need a grid size in the X direction and a grid size in the Y direction. So I've picked some values, 50 and 30, because I think that these will work fine on our scene, but you can adapt them to your needs. And we also need to have a size of our grid cell. So let's create a cell size of 2, and we make it into a float, so we can have some smaller values like 1.5 or whatever value is good for you. Okay, then we will need some type of structure to keep this information about our node system. So we need to create a new class, and we can do it through Visual Studio as well as doing it through Unity. So let's go on Add New Item in our A star folder, Add New Item, and then we select class and we rename it to A star node, and we press Add. Now we have created this class from within Visual Studio, and it adds this namespace which we actually don't need. So let's remove that, and let's just move it out, and we'll make it into a public class, A star node, and then we can get rid of all this extra stuff that we don't need. So this will not be a mono behavior class because we don't need that, and we will do it using a little bit of I would say lazy programming, but it works for us in this need. We will make every sort of variable public so that we can use it anywhere without using a get and set function. And we have an error already, and it's because we're not using Unity's engine. So let's use that, use Unity engine. So the first thing we have is our grid position. That's a X and Y direction, and we're using a vector2 integer, so that's just integer values. And then what we want is we want to have the ability to have neighbors, that each node had a possibility of having neighbors. So let's create a list of other A star nodes, and we'll call them neighbors. And what we need to as well know is this node an obstacle or not? So we'll add a isObstacle, which has a default value of false. And then we had these different costs that we had that we want to be able to calculate later on. So we had a distance from start point to node. That was the G cost. So let's add that one. And then we had something called an H cost, which was the distance from node to goal. So we'll add that. And then we had the total cost. So that was the F cost. So let's add that as an integer, F cost total. And then we had this thing that I called a pick order that we also needed. So let's add that pick order. And then we want to also as well know if we have already sort of calculated our cost. So we need a state variable for that. So let's have a is cost calculated, and it's false when it hasn't calculated the cost. And what more? I think that's enough as a starter. And then we want to create a constructor for this. So a constructor is a way of creating a version of the class in a more easier way. So let's add that. And so when we are creating the class, this function will be called as the constructor, and it has a value of grid position as the start. So we'll take a parameter. So let's take this parameter and assign it to grid position. Perfect. So that's just the first part of our class. So let's save that and go back to our A star light version. And from this, we want to be able to create a debug version. So we want to quickly be able to see what we're doing inside Unity. So we can get rid of our update function because we will not need that. And then we need to use our A* node that we just created, and we will create a two-dimensional array that will hold this. Here's an example from our game. So it's like Arcade Racing, which uses this component. Then we want to find the game on Steam where we can Nintendo Switch our grid. Please take it for a spin if you want to. So the first thing we need to do is allocate space for our array. So let's do A* nodes, and then we create a new and A* node with the size of the grid. And then we want to populate it with our nodes. So what we do is we create a for loop, and we go through on the x-axis from 0 to the size of the grid, and do the same thing on the y-axis. That will create a grid for us, and we will create our nodes in here. So we take our nodes in the coordinate system x and y, and then we create our node and give it that position, so it knows its own position. Excellent. Then when we're doing things like this, we need to also call it when we start. When we do things like this, we want to debug it so we can see visually what is going on. And in Unity, there is a nifty little function called onDrawGizmos that is only shown in the editor. So anything that is drawn in here is shown in the editor. And it is actually running all the time. So what we need to do in this case, because we're going to draw these nodes, is we need to check that it's been initialized in this start function. Because otherwise it's going to run while we are in the editor mode and haven't started the game yet, and that will produce a bunch of errors. So let's check for that. And then we want to draw our grid. So we run through our array like we did before, but there is one little thing, and that is this grid has its own position system. So it is using its own coordinate system that is not the same as Unity. So we need a function to change this so it actually works well in Unity. So we will create a convert function. So we will call it convert grid position to world position, and it takes in an A* node. And then it needs to return a vector 3, a position. So what we do is we take our A* node, grid position.x, we multiply it by the cell size, and then we reduce half of this cell size. So what happens here is that by doing it this way, we are changing the position of the grid. So we're offsetting it so it becomes centered on top of the course. And then we do the same thing on the y-axis, and we feed in 0 in the z value. Cool. Now we can actually draw our little gizmos. So we'll draw it in the color green, and we will use the built-in function drawWireCube. And the reason why we're drawing a cube is because there is no 2D functions for this. So we're going to draw a wire cube instead. But since we are in 2D, it will look like a 2D version of it anyway. All right, so this takes in a center value and a size. So our center is going to be our node that we're currently on, but we need to convert it to our world position. And then we need to feed in a size. So the size of our box or our wire cube is going to be the same as the cell size. Okay, so if we now, there is a missing parenthesis. If we now take this and run it in Unity, we should get a nice green grid. So let's try that. So if we take our AI player and we open the prefab variant and we assign the A* light script to it and we press play, then we should get a nice green grid. All right, awesome. So now we can see that we have our grid and our node system is starting to work. So now we need to do some enhancements on the node system. So let's go back into our A* light script. So the first thing we want to do is when we are creating our grid, we want to be able to see if there's an obstacle in this node or not. So what we do is we take our this grid position that we have here. So we want to convert it into a world position. So we'll use our function, convert grid position to world position, and fit it with our node. Now that we have it in the regular Unity coordinates, we can check if there's something in the way. So what we do is we use physics.overlap_circle with the world position, and then we'll take half of the cell size. So that will create a circle that fits inside our grid node. And it will return a hit collider 2D. And if that hit collider is not null, then it means that we hit something. But there are a few things on the course that we shouldn't consider as an obstacle. For instance, other AR cars are not going to be an obstacle for us. So what we do is that we check if the hit colliders transform.root has the tag AI. In that case, we will just continue. So this function will continue to the next section in the for loop. And we do the same thing to check if there's a player in the way. Then we are just proceeding and saying that we don't care, we ignore the players. But if it's neither of them, then it's gotta be an obstacle, because that's what we have left in our scene. So in that case, we will mark it as an obstacle. And if we go down again to our onDraw gizmos, we can enhance this a little bit and say that, okay, if our star node that we are on here is an obstacle, then we're going to draw it in red. And if it's not an obstacle, we're going to draw it in green. So let's save this and run it in Unity. So now we can see that our grid is drawn and certain sections are red, and that's because it has detected an obstacle. And as we can see, this part here is showing the whole area as an obstacle, and we might have to change our grid size a little bit if we don't want this. But for this demo, this is not a problem at all. So let's go back into our script, the A* light, and add some more parts of the algorithm. So then we can get back to our algorithm, and one important part of the algorithm is the ability to keep track of the neighbors. So after we have created our or updated which nodes are obstacles or not, we're going to loop through them again. And this time we are going to start with checking the northern part of this node and see if there is a neighbor. So we are mindful that we are not going outside of the grid, so the value should be larger than 0, otherwise we are outside of our grid. And we are checking that, okay, it's not an obstacle, and if it's not an obstacle, then we can add it to the list of neighbors. Then we do the same thing for the southern part, but in this case we're mindful that we're not going outside the grid in the other direction. And then we do the same thing for the east and west. And once we have done this, our method is ready to actually start to finding the path. So now we can actually start with our pathfinding function. So let's add a new function, and we'll call it findPath, and it will take in a vector2 destination, and it will turn a list of vector2s. That's going to be the path that the AI is going to follow. So the first thing we need to do is the same as when we did the gizmos, is make sure that there actually is a grid of star nodes. If it's not, then we're going to return null. So we have to be mindful that this function can return null. And then what we want is we want to start from our destination. But as we probably remember, this is a different coordinate system than our grid is using. So the same as we have a convert grid position to world position, we need to reverse that. So we need to have a convert world to grid point. So we add a new function for that. And all right, messed up the formatting a little bit. There we go. So we'll call it convert world to grid point, and it takes in a vector2 position and it returns a vector2 int. This is going to be in the grid coordinate system. Then we calculate the grid point, and we do the reverse operation of this. So we'll take our position, we divide it by the cell size, and then we add the grid size divided by 2, and we round the whole thing off into an integer. So that will create our nice little point. And then we do the same thing for the y-axis, and then we return it as a grid point. So now we have the ability to convert world to grid point and also convert the other way around. So that's awesome. What we now want to do is we want to take this destination and we want to create it or change it into the same coordinate system that the grid is using. So let's start by converting those. So we'll convert the destination first, and while we're at it, we can make it easy for us and also take our current position and convert that into a grid point. So we'll take the transform's current position and do that. Then we want to fetch our first node so that we know where we are. But as I explained earlier, it's also nice to have some debug values. So we'll start by actually going to the top and adding some variables for that as well, so that we know what's going on and we can debug it through our gizmos. So we'll have a start position debug, destination position debug. And we'll just make them into large values as a start, and then we can actually update them when we come along. So here we have again our find path function that we're working on, and we'll set our nice debug output. So the destination position is going to be our destination, and then we actually want to find our start node. Not only the position, but the actual node. So we need a helper function for that as well. So let's create a new helper function called getNodeFromPoint. So it will return an A star node, and it will take in a vector2 integer, the grid point. And what we need to do is we need to make sure that, again, we are not stepping outside of the boundaries, because that will just produce errors. So it's better that we return null in those cases. But if we are within the grid, then we can actually return the actual grid value. So we'll take our grid point X, our grid point Y, and return the A star node. Awesome. So now we can take our start node, or we will create a start node. So that we keep track of that one, and then we can actually find it here in our find path. So what we will do is that we will use our new function, and we will get the node from point, the current position on grid, and we will assign it to start node. Excellent. And then we want to be able to debug it as well. So let's store it as a debug value. And we'll take the start position and we'll convert the grid position to world position from the start node. All right, so perfect. Now what we want to do is we want to be able to display the start points. So let's add that to our debug function. So let's use our draw gizmos. So after we've drawn our grid, let's draw the start position in a color black, and then we want to draw our goal position or end position in the color red. Okay, so if we now make sure that this returns a value, so for now we will just use return null. And now we can at least try it in Unity and see that we get a start and end point to our algorithm. But before we use it in Unity, we actually have to call the function as well. So let's go to our start function, and we'll just pick a value that is on the right side, 32 in the X and 17 in the Y. Perfect. So now we can try that. Okay, great. So now we have our start position as the black dot and our end position as the red dot. So let's go back into Visual Studio and add some more in the algorithm. So in our algorithm, we want to be able to keep track of the nodes that we have already visited and the ones that we should look into or investigate. So we will use two lists for this. One is a list of A star nodes, and we call it nodes to check. And the other one is another list with A star nodes, which we call nodes checked. So if we go back then and look at our code, we now have our start node, which is the first node that we will sort of investigate. And we want to create a loop for this, so we can loop through all of the neighbor nodes. So we will start with the current node, and we say that, okay, initially that will be our start node. And what we will do is we will have a way of controlling our loop that we're going to do. So we want to have a way of exiting it when we have found a path. And we also want to keep control over the pick order that starts with 1. Okay, so now we can start our loop, and we're going to use a while loop. And what we say in our while loop is that, okay, while we are not done finding path, then we're going to loop. And the first thing that we want to do is we want to remove our current node from nodes to check, because right now we are checking this node, so we can remove it from the nodes to check. Then we want to set the pick order of the current node, and then as we will iterate, we want to make sure that the next one is going to get a higher pick order. Okay, so then we are adding this node to our checked node, because we have checked this one. And what we want to check as well is, okay, are we finished? Have we reached our finished point? So is the current node grid position equal to the destination grid point? If it is, then we are actually done, and we use a break function to exit this loop. If we are not done, it means that we need to calculate the cost of the current node and its neighbors. So we need a new function for that. So that function is best to create on the A star node. So we'll add a new function, and we will call it calculate costs for node. And it takes in a vector2 integer, the AI position in grid space, and another vector2, which is the destination. And what we want to check first of all is, have we already calculated the cost? If we have, then we don't need to do it again, and we can just return. If we're not, then we want to calculate the G cost first. So the G cost is the distance from start. And how we get that is by checking two values. So we are calculating, okay, how many steps are we away from the grid position, the node's own grid position, minus the AI position. And then we add the value of the grid position Y minus the AI position Y. So we're checking the X position and Y position, and we're adding them together. And then we have the H cost, which is the cost distance from goal. And we will do a similar thing. We will take the grid position of the X value minus the destination of the X and do the same on the Y. So that's the cost of that. And then the total cost is just to add them together. So when we have done that, we can see that, okay, yes, our cost is calculated and we are done. So now if we go back into our A* Lite version, what we want to do is we want to create a similar function. So we will call it the same thing and calculate cost for nodes and neighbors. So we take in a start node, the AI position and the destination. Then what we do is that, okay, the first node that we got, the A* node, let's just calculate the cost for that. And then we run a for each loop. So we run through all of the neighbors that this node has. And what we do is we do the same thing. We are calling the function calculate cost for node. Okay, so perfect. Now we can proceed in our loop. So let's just use this like that. Calculate cost for neighbors with the current node and the current position grid point and the destination grid point. Okay, so what we have then is that, okay, we need to consider which one is going to be our next best option. So what we will do is that we will run through all of our neighbor nodes in our current node. And what we will do first of all is that we will skip any node that we have already checked. So that was our criteria. We should not pick a node that has already been checked. And we should not check any node that is on our nodes to check list either. So if it's on that list, then we don't need to add it again. And what we do then is that we decide, okay, this node should be on our list to check. Okay, awesome. So now that we've done that, we need to decide, okay, which is going to be our next node that we will actually look into. So we will use some sorting methods, and first of all we need to use add that using system link. Okay, so now we can sort, and what we do is we use our nodes to check and we order by, and we use a lambda expression saying that, okay, it's going to order by the total cost and then by the cost distance from goal, because that was our second criteria that we had. And this will return a list, or we actually call it two lists, so we get a list out of it and we assign it to our nodes to check. So if we have now sorted this list, and if the list actually contains some values, then we can proceed. But let's add a safeguard saying that, okay, if there is no nodes to check, the count is 0, then we have no nodes left to check and we don't have a solution. So we return null in that case and we debug log a warning. Otherwise, it's going to be quite easy. Our current node is equal to the first node because we have sorted it already in the order we want to. So the first node will be the best choice. Perfect. So this is where this will actually loop again. So let's close the while loop. So it will run once more. And it will do the same thing all over again until it has either reached the endpoint or there are no nodes left to check. So this is not very interesting to look at though. So what we want to do is add some debug functions so we can see what's going on. So we go down to our gizmos again, and the first thing we do is we do a for each loop and we run through all the checked node in the nodes checked, and we will draw a sphere in the color of green when we find those. And then we will do the same thing for the nodes that we have left to check, and in this case we will use a color of yellow to draw them. Okay, so if we save now and take it for a spin, it should display either yellow spheres or green spheres. And voila, it works. We have the start position, which is our black node. We have the red position, which is our end goal. We have the yellow, which was the ones that it should check or could check, and the greens that have been checked. So we can see already it has found a path to our end position. So that's awesome. Now we have left to do is this pathing back so that we can actually find our way back the quickest route for our AI. So let's do that, and we'll go back into Visual Studio again. So for us to create this path back for the AI, we create a new function. So let's go and we call it create path for AI. And it will return a list of vector 2s that is going to be in the world coordinates that it can use to actually just run through and find its way back. So first of all, we need to create a list that it can return. So result AI path. And then we're going to take our nice list that we have the nodes that are checked. And as we did it when we went through the theory behind it, we will reverse it. So we will start at the finish point instead of starting at the starting point. Okay, so then we will do a similar thing that we did when we were looping up here with our while loop. We will do the same here. And we will have a sort of a variable called isPathCreated. And it's going to start with false. And then we will pick our current node as the first node in our list. So it's going to be the destination node. And then we will just add a failsafe here, and it will be that we have a certain number of attempts to actually manage to solve this, so we don't get stuck in an endless loop. And then we go into our while loop, and we are going to say, okay, so while isPath not created, then loop. And let's add our attempts ++, so we increase that value. And we are going to make sure that if we have a very high number, let's say if we run more than 1,000 attempts, then we're gonna just return a sort of a warning, and we're gonna break the loop. And then of course we need to return a value as well. So let's return the result AI path that we have. Okay, so the function now sort of works. It doesn't really do anything. It will just come in here, pick the current node, and then it will loop for 1,000 times and display this error. So what we want is for it to do some more clever things. So what we want to do is loop through backwards from our destination. And what we wanted to base this on is the pick order. So what we take is our current node and its neighbors, and then we are ordering it by the one that has the lowest pick order. So we will run through this backwards. So that will be our best choice to actually reach our starting point. And what we do then is we are going to as well pick the best out of this that we have ordered them. So we will run through all of them in a for each loop. And I just messed up more formatting. There we go. And so what we're going to do is we're going to make sure that our AI node or AI path does not contain the node already, and that the node checked actually has this node value. That's our criteria for it to be considered. Then what we will do is we will add this to our AI path list, or results AI path. Sorry. And we will add the current node. Oh, and there's an error because I have forgotten to add this AI path. So we need to create that as a list of A* nodes. That's going to be AI path. So now we can actually use that. And so if this is true, this statement, then we will add our A* node to it. And the current one is our A* node now. So after that we can break the for each loop because we have found what we're looking for. And then we also need to have a way of exiting the whole loop. So if our current node is equal to our start node, then we are done with creating our path. But we also need to populate our result AI path. So we do that again by using a for each loop where we go through the AI path and we take each node and convert the grid position to world position. And the final part is that we need to flip this path, the result AI path, because it's from the destination to the start and we want it to be the other way around. So let's add this to our gizmos so we can draw that as well. So we'll take it and draw it after we've drawn the nodes that we should check. So we store the last AI point and we start at the position 0, and then we add just a way of skipping the first point because we don't really want it to show a position that starts at 0. And what we will do is we will draw an AI path. So we will go through our we actually haven't called the function yet, so we need to do that as well. So let's create a list of our AI path because we're gonna need that. And then we'll go to our list here and we are going to say that, okay, our AI path, and then we use our create path for AI with the current position grid point. Okay, now we can continue with our nice debug function. Okay, so what we have is that we want to be able to draw this path, and we're going to use the line gizmos for that. So we'll make it black, and we're going to then go through our list with a for each loop. And what we will do is we will see that, okay, if it's not the first step, then we're going to draw a line from the last point to our current point. And we need to set this last point is going to be our point. And then we're going to set to is first step is false. So if we save it and run it now, we should get a nice path. Okay, so now we get a nice path from the start. It goes up here and it goes above the obstacle and around it and exits here. But it should exit there. So there's some type of bug in our code. So let's fix that. Now the reason for this bug is because how we are doing our loop when we are creating our path. So what we have is our is path created. So let's start by actually adding the first part to our path. So that was not added when we were doing this while loop. Okay, so perfect. Now we solved that problem as well. The only problem that we have left to solve is that the car is actually not using our path at all. So that is something we need to change in the AI code for the car. Now let's go to our scripts and open the car AI handler. So in our car AI handler, we need to add a couple of variables. for our stuck handling. So we want to be able to tell if we are running our stuck check or not. And this will be a coroutine, so that's why we need to know if we have started it already or not. Then we want to know if it's the first temporary waypoint, and we want to have the ability to check how many times have we run our stuck check, and then our temporary waypoints that we get out of our function, the A* function, when we are finding the path. Then we need a reference to our A* light. And we also need to get the component for that, and it's attached to the car, so we can just use get component. And then we want to create a coroutine. So let's go to the bottom, and we want to create something that we call a stuck check. And what it will do is it will take the initial position of the car and store that, and then it will update that it's running. So is running is set to true, and then we will simply wait for a period of time, 0.7 seconds, and this can be adapted to your game. And after we have waited for that duration, we will check, okay, have we moved enough to consider that we are not stuck? So we need to have moved larger than the square magnitude of 3 to say that no, we're not stuck. But if we are stuck, then we want to have the A* find the path for us from the current, or rather to the destination of the current waypoint transform. So that's what we want to go to where the waypoint is currently at. Then we have to handle some edge cases. So what happens if the temporary waypoint is returned as null? So we check that. Is it null? In that case, we are returning an empty list, because then we don't really know where to go anyway. And then we'll update our stuck check counter and say that, okay, we're adding, because we have just performed it. And we are also saying that, okay, now that we have done it, this is the first temporary waypoint. So if we are not stuck, then we can simply update our stuck check counter and say that it's 0, we're not stuck. And then we can say that as well, that we are not running our stuck check anymore. Okay, awesome. So what we want to do is we want to be able to call this. So we go up to our fixed update. Here we go. So in our fixed update, we'll add that, okay, if the top-down car controller has a velocity of less than 0.5 and we are applying throttle forward, then we want to start running our stuck check. And we're checking that we're not already running it. And then we are using our start coroutine and we're running it. So this is nice, but if it has started running the stuck check, then it will actually not run it again, because if the velocity is larger than this value, so we will need to run it once more if we have looped it a couple of times. And this is an edge case when we are going to add reversing to it. So we need to have our stuck check counter, and if it's larger than 4 and it's not running, then let's run it again. We'll come into this why we need it later on, but it's how we handle that the car is able to change direction later on. Okay, so if we save this now and take it for a spin in Unity, it should request a path if the car is getting stuck. So let's see that it works. So now we can see that it actually calculates the path once it gets stuck, but then it freaks out after a while and fills the whole screen with these green dots. And the reason for that is, since it's still stuck here, after 0.7 seconds it will calculate the path again. But our A* routine that we have created is not meant to be called twice. So we need to add an improvement to this so it can handle the ability to reset itself, so it can calculate a brand new path. So let's stop our script from running, and then we open our A star node. So in our A star node, we need to add a new function to reset it. So let's add a public void reset. And we reset all the cost calculations. We will keep the information about the neighbors because that will remain the same, so we don't have to redo that anyway. And then we go into our A star light, and similarly we need a reset function here as well. So after we create our grid, let's add a reset. And what it does, it clears the nodes to check and the nodes that we have checked, and also the AI path. And then it loops through the whole grid and calls reset on our nodes. So this reset function is something we want to call when we are actually doing our find path. So before we can find the path, let's reset the whole system so we can start from a fresh situation. So if we save now and try it in Unity, it should work much better. So now we see that the path is calculated once and it doesn't fill up the whole screen with green dots after a while. So our reset function is working just fine. So now we have only one thing left to do, and that is to continue to enhance the car AI script to make sure that it's following the temporary waypoints that we have created. So let's open our car AI handler again. So in our car AI handler, we already have a function for following waypoints. So let's add a new function to follow our temporary waypoints. There we go. And what we want to do is when we are following our waypoints, we can set our target position to be our temporary waypoints. The first item in it is going to be our target position. Then we want to set, okay, so how close are we to our target? So we'll store the distance to the waypoint. And then we want to drive a little bit slower than most of the time. So we're setting our max speed to 5 so that we can get a little bit more control over the car. And then we want to have some minimum distance. Okay, how close are we going to be to consider that we have reached the waypoint? So we start with 1.5, but we only need that for really the first waypoints, because the first waypoint is essential that we hit. The other ones we can have a little bit larger distance to avoid, jittering and stuff like that. So then we make a check. Okay, so have we gotten close enough to reach the waypoint? If we have, then we just remove it from the list. And we set that, okay, it's not the first waypoint that we have reached. Okay, perfect. So now we need to call this function as well. And what we do is we look at, okay, AI mode follow waypoints. So we'll enhance this one and say that, okay, if there are some temporary waypoints, then we should follow them. So if the count is 0, then we don't have any temporary waypoints, so we'll just follow our regular waypoints, and otherwise we're going to follow our temporary waypoints. So now this will actually work, but often the problem is that the car is driving straight into an obstacle and it's heading straight into it. And for our car right now to be able to get out of the situation, it needs to learn how to reverse as well, because right now it's just trying to go forward. So this car will still be stuck even though it's getting a new waypoints to get out of the situation. It's actually not using them. So let's look at our function that is applying our throttle to the car. And we have this apply throttle or brake. And what we want to do is we want to make it a little bit more clever. So if we have some temporary waypoints, then we want to handle it differently. So what we want to do is, especially we want to check, okay, what is the angle to our target? Is the target sort of behind the car? And we can do that by checking the angle to target if it's greater than 0. And then we can set the throttle should be -1. And If it's in the other direction, then we can also do that. But there are some errors because we haven't set our angle to target. But there is actually already a variable for this. So if we look at our steering function, turn towards target, we can see that, hey, here we have an angle to target. So what we do is we just make this into a global variable instead. So we'll go up and we'll fix this by adding it to our stock handler and saying that, okay, float angle to target is 0. Okay, now we resolved one of the problems. The other one problem is that we have not declared our throttle. So before we do this, let's add the throttle up here, and we will use the same function that we are actually returning here. The only difference is that we want to be able to reverse the car. So if we change this with return throttle, then it will work. And we do have another case where we want it to actually reverse as well, because let's say that we have an angle to target that is actually not behind, so or sort of less than 70 degrees, so it's like maybe 20 degrees. But for some reason the car is still stuck after a couple of attempts to get it free. So in that case we say that, okay, if we are have our stuck counter, stuck check counter is larger than 3, then we will reverse anyway. So here is that thing that we added before, that we have the ability to actually reset it once it gets free. So if we save this now and run, then the car should be able to handle the case and get, well, free itself and follow the path. But there is still one little problem that we forgot about, and that is that I rigged the A-star light function to actually not work properly with our find path. Because to avoid an error, so we could actually test run it before, I rigged it so it will always return null. So that's not correct. So that will cause it to never actually find the waypoints. So the AI path needs to be returned here, and let's save that, and now we can take it for a spin in Unity. So now the car hits the obstacle, it checks for a path, reverses, and traverses the path until it reaches the end of the temporary waypoints, and then it gets back into, well, moving along the regular waypoints. So this actually is the implementation that we had in mind for the A-star, and we will do some tiny cleanups to support additional cars, and also to get a little bit better debug information if we need it later on. So let's stop here and go back into our A-star light again. Now, if we are going to run multiple cars, then all of them will be drawing debug information on the screen, which will flood it fairly quickly. So let's add a variable to control that. Is debug active for car? And then we go down into our gizmos, and we check that if our debug active for car. If it's not, then let's just return. Okay, so great. Now what we want to do as well is maybe we want to get a little bit more information on our checked gizmos. So our checked nodes have a lot of information that could be interesting to draw instead of just this green information or these green spheres that are being drawn right now. So we have the ability to actually write information in the editor. So we have the ability to actually write debug information in the editor, and to be able to do that we need to start using Unity editor. And then if we go down into our debug again and look at, okay, we want to draw some information here. What we want to do is, I'm just quickly adding this. We want to use a label position that is the node, and then we just put it slightly above in the Z direction, and then we create a UI style so we can change the text color, and then we are going to write on the position of the node in the minus 0.6 and slightly above. We're going to have the H cost in green and the G cost in red, and our pick order in yellow, and the total cost in white. So with this, we can actually debug a lot more and see exactly how our star system or our A star system is calculating, and that it's working perfectly. However, when using handles, we need to be a little bit careful, because this will only work when we are running inside the editor. So if we create a build out of this, it won't actually work, because it will throw an error. So we need to make sure that this is not included when we are doing a build, and then we can use this to check if Unity editor is defined, and if it is, it will actually include this in the build. And if it's not, then it will be removed. So if we make a standalone build for this to run on, let's say, PC, then this part will not be included. Okay, awesome. Now we can try this in Unity again. So if we select our AI car and enable debug for it and hit the play button, then once it hits the wall, we can see more debug information. And now it looks the same as when we went through the theory behind A star. So we have the white part, which is the total cost. We have the green part, the green value, which is the cost to reach the end, the destination. So let's check that it's correct. 1 tile, yes, it's correct. And then we have the value 9, which is the number of tiles to reach the start point. So let's see if it's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it's correct. And then we have the pick value, which is used for the path to create the reversed path. So it will follow the lowest value. So we can see that, yeah, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10. And then it goes down into 5, because that's what we said. It would take this node here and look at, okay, my neighbor, which has the lowest pick number. It's 5. Otherwise, it would drive from number 10 to number 9 and number 8. And I don't even see number 7. Yeah, number 7, 6. So it would drive like crazy. So instead we have this nice path, and then it has been deleted here because the car has already started to use that path. So that's fine for us. And yeah, so the cool part is we can now use this with lots of cars. So let's try that. So I've added a bunch of AI cars and made the course a little bit harder for them to navigate. So we can see that they are getting stuck, especially in this section, but they are able to find a path and get out of it. They are not playing very nicely with each other, but it works fairly well now that I've changed the collisions so they don't get stuck so much in each other. And we can enable the debug whenever we want to have a look at a specific car to see, okay, what path does it have and what solution does it have to find its way to the waypoint. Okay, so this concludes today's tutorial. Now, I hope that you enjoyed this video, and if you did, please give it a thumbs up. And also please consider hit that subscribe button if you want to get a notification when the next video is out. I'd also like to give a special thanks to all of our Patreon supporters, and especially MSGS Europe that has reached the WOW level in our benefits on Patreon. The link to our Patreon page is in the description below, so please consider supporting us there. Here's an example from our game, Total Arcade Racing, which uses this component for its physics, inputs and other parts. You can find the game on Steam, Xbox and Nintendo Switch. Please take it for a spin if you want to.